Ever wondered how windshield wipers move or how robot arms grab objects? The answer: linkages. A linkage is a set of rigid links connected by joints like your arm's bones and joints. They transform motion. Think scissors, reclining chairs, or the powerful arms of construction equipment. The most common type is the 4-bar linkage. 4 links, one fixed, one driven, 2 connecting the motion. By adjusting link lengths and joints, engineers create almost any movement imaginable. Let's dive in and see how we analyze their motion. Why do engineers care about how fast linkage parts move? Because speed and acceleration determine if a machine works safely and efficiently. Move too fast, and you risk breaking delicate parts. Too slow, and you lose productivity. Acceleration causes internal forces. Too much, and parts can bend or break. Velocity and acceleration analysis help engineers predict these forces, choose the right materials, and design machines that last. It's not just math, it's the key to safe, reliable engineering. Let's dive into the fascinating world of mechanical linkages by analyzing a 4-bar linkage system. This system consists of 4 interconnected links, with link 2 rotating at a constant speed, setting everything in motion. Our objective is to determine the velocity of key points using a velocity diagram, a visual map that shows both speed and direction. Imagine link 2 is 0.5 meters long and spins at a rate of 2 radians per second, creating a dynamic motion. The velocity at point A, which is the joint, measures 1 meter per second, and it is perpendicular to link 2. To find the velocity at point B, where the coupler meets the follower, we employ geometry. Its velocity must be perpendicular to both link 3 and link 4. By drawing vectors for these directions, we can pinpoint their intersection, which provides us with the solution. This graphical method is a powerful tool, allowing us to solve for unknown speeds quickly and efficiently. By accurately measuring the vectors, we gain insight into how fast every part of the mechanism is moving. That's the incredible power and utility of velocity diagrams in mechanical engineering. Let's talk about acceleration, the rate at which velocity changes over time. Acceleration isn't just about going faster or slower, it's about how quickly that change happens and in what direction. In machines, this is a crucial concept, as every moving part experiences acceleration in some form. Acceleration actually has 2 distinct components: radial acceleration, which comes from changing direction, and tangential acceleration, which results from changing speed. Both play unique roles in mechanical systems. For a rotating link, the radial acceleration always points toward the center of rotation, keeping the motion curved. Tangential acceleration, on the other hand, only appears if the speed of rotation is changing, if the link is speeding up or slowing down. In our example, link 2 spins at a constant speed, so point A experiences only radial acceleration, which is calculated to be 4 meters per second squared. There's no tangential component here because the speed isn't changing. For point B, we use a similar vector diagram, but this time we combine both radial and tangential components. This helps us solve for unknowns and understand the complete acceleration at that point. By combining geometry and physics, we can reveal exactly how every part of the mechanism accelerates, ensuring smooth and efficient machine operation. We've seen how linkages transform motion, turning simple inputs into complex, coordinated movements that drive the machines all around us. That's why analyzing speed and acceleration is so crucial. These factors determine not just how fast something moves, but how smoothly and safely it operates. By using velocity and acceleration diagrams, engineers can predict exactly how machines will behave under different conditions long before they're ever built. This lets them ensure every mechanism is not only efficient, but also safe and reliable for everyday use, preventing costly breakdowns or accidents. The 4-bar linkage is just one classic example of these principles in action. But the same ideas apply to engines, robots, manufacturing lines, and countless other machines that shape our world. By breaking down motion into vectors and diagrams, we turn what seems like a complicated puzzle into something we can visualize, understand, and solve step by step. So next time you see a machine in action, take a closer look. Try to spot the linkages and moving parts behind the scenes. Imagine the hidden math and physics at work, quietly guiding every movement and interaction. That's the heart of engineering. Curiosity to ask questions, analysis to find answers, and creativity to invent new solutions. Keep asking yourself, how does it move? How fast? What makes it work the way it does? When you do, you're not just observing, you're thinking like an engineer ready to shape the future.